Swayam Prabha. Digital India. Educated India.
So, last class I have discussed that how you will get the equation for beam resting on two parameter model. Then I discussed also that what are the differences between the beam resting on two parameter model and beam resting on spring or one parameter model. Okay, and under different condition, that means under beam under plane strain condition or beam with finite width, you have to modify the B dash or B star value and E star value. And I have given the equation for both the conditions, that means beam resting on spring and beam resting on two parameter model. Now, today I will discuss how we can solve these equation by using finite difference method. Okay? And because I have already given the idea that how you can solve the infinite beam and semi infinite beam in case of beam resting on spring. Okay? And the similarly you can do it for the finite length beam also, and for two parameter model also you can solve and you will get the closed form solution. But as you will go for one parameter model to two parameter model or beam resting on spring to beam resting on two parameter model, your solution technique will become more complex. Okay. And for example, here most of the soil parameters are considered linear. Okay, or the stress strain behavior is considered the linear, but if we want to incorporate the nonlinearity, then also getting closed form solution is very difficult. So, in such case we can take the help of numerical methods, and that is, and I will discuss the finite difference method only. So, that means here for you can see that getting solution for closed form solution for infinite beam is easier compared to the semi infinite and compared to the finite length beam also. So, that means infinite is most easiest solution procedure to get the closed form solution, and as you go for the finite length beam or I will go for the beam on two parameter model or I will incorporate the nonlinearity, then the solution will become more complex. So, in such case getting closed form solution is difficult. So, we can go for the numerical too. So, now first I will discuss that what is how I will get the finite difference coefficient. Okay. So, the finite difference method I can write by Taylor series that I can write that f x plus h is equal to f x plus h 1 factorial f single dash x, then plus a square f double dash x h cube x and so on. So, now if I neglect these terms, okay. So, now if I neglect the h square onward terms, I can write that h f dash x is equal to f x plus h minus f x. Okay. So, now suppose you have a beam at this point and that is called say ith point, this is I plus 1 point, this is I minus 1 point, and at ith point your deflection is W I and I plus 1 point your deflection is I plus 1 and here deflection is I minus 1. and the distance between this node or the points is h. So, that means we have divided these beams with number of nodes and each node has its name. So, that is the ith node I plus 1 and so on. So, last node will be the nth node and the first node will be the first node. Okay? And deflection of each node, because when we apply the load there will be deflection, and deflection of each node you can write y also, and here deflection is written as w. So, wi plus 1 and wi minus 1 to w1 and wn. So, this is the deflection of each node. So, now I can write these equation in terms of this deflection is, this is f dash x, that means I can write dy dx, and that is equal to f x plus h minus f x by h, or I can write that dw dx, that is equal to w I plus 1 then minus w I divided by h. So, this is called forward difference scheme. Method. Okay. So, that means here we are going in forward direction. So, this way I can write dw dx in finite difference form, and that is forward difference scheme. Now, similar to Taylor series, if I write these expression f h minus a h, f x minus h, then I can write this is f x minus h f dash x plus h square f double dash x minus h cube 3 factorial f 3 x plus so on. Now, again if I remove or neglect this h square term, then I can write that h f dash x, that is equal to f x minus f x minus h, or I can write that dw dx will be equal to wi minus wi minus 1 divided by h. So, this is called backward difference method. So, here we are going in the backward directions, okay, I to I minus 1. Okay. Now, if we have, this is equation number 1, this is equation number 2. Okay. And if I add these two equations 1 and 2, then I will get that f x plus h plus f x minus h, that is equal to, we are adding, that is 2 f x, then this will cancel out, plus 2 a square, then f double dash x, then plus, then h 3 will also cancel. So, there will be f to the power h to the power 4, then 4 factorial, and again this will be 2, then f 4 x, okay, and so on. So, now I can, if I neglect, now if I neglect this term, okay, 4th term, then I will get that this 2 will cancel out. So, this will be a square f dash x, that is equal to f x plus h minus 2 f x plus f x minus h. So, I can write this is f double dash x. So, d square w d x square, this will be W I plus 1 minus 2 W I plus W I minus 1 divided by A square. Okay? So, this is called central difference method. Because here it is central, we are taking W I plus 1 as well as I minus 1. This is called central difference method. Now, if I subtract 2 from 1, then I will get f x plus h minus f x minus h, that is equal to subtracting that. So, this will first term will cancel. So, this will be 2 h f dash x plus 2 by 3 factorial f 3 x, and this is h cube. Okay, so, I should write this is 2 h cube, 2 h cube. Now, if I neglect this h cube term and higher, then I can write that f double dash x is equal to, or 2 h double dash is f x plus h minus f x minus h, or I can write d w dx is equal to w I plus 1 minus w I minus 1 divided by 2 h. H is the difference between this node. So, now this is also called central difference scheme. So, you can see that in central difference scheme we are neglecting h cube and higher, but in forward and backward difference scheme we are neglecting h square and higher term. As h is very small value, so if I using the h cube and higher, so basically our error is less compared to when we are neglecting h square and higher term. Clear? So, in that sense the central difference scheme is less erroneous compared to the forward difference and backward difference scheme, because the here obviously there are some errors, because we are neglecting some terms, because our aim is to get the solution which is very close to the closed form solution. Obviously, closed form solution will give me the actual solution, but sometimes as I mentioned it is very difficult to get. So, that is why we are taking the help of numerical tools, and our aim is to get that closed form solution as close as possible, because you can see we are neglecting some terms. So, definitely there are some errors, but if I use the central difference scheme our error will be less compared to the backward and forward difference scheme. And one more thing I want to mention, that do not mix these two schemes when you using them in your problem. You use them always, you try to use the central difference scheme in all the cases in a particular problem. Okay. So, now let me apply this problem or this finite difference scheme. So, for a beam problem, so beam on Winkler's spin. So, beam on Winkler's spin, and it is a finite beam and it is a free end beam. Okay? It is a finite free end beam. Both the ends are free ends. So, I can write this is A point, B point. So, moment at A will be 0 and shear force at A will be 0. Again moment at B will be 0 and shear force at B will be 0, because it is a free end beam. Okay. So, now my basic equation is your E I d 4 W dx 4, because now it is E star plus, because it is a Winkler model. So, whether it is on two cases, it will be always B. So, B k 0 W, so that is equal to Q. Okay. So, now we are taking that infinite length. So, that means in such case beam with finite width. So, beam with finite width, my B dash will be equal to B and E dash will be equal to E. Okay. So, I can write this is beam with finite width. So, I can write this is E I d 4 W d x 4, this is, and we can write this is your B and this one is this one is plus k 0. So, this is plus k 0 W, that is equal to Q by B. Okay. So, that means in such case your Q is equal to kilonewton per meter square. Okay. So, Q is kilonewton per meter square divided by B. So, now it will be kilonewton per meter, and here also you can see that this is your no, this is again Q is equal to kilonewton per meter. Okay. So, that finally it will be kilonewton per meter square unit. Q is in kilonewton per meter. Okay, this is the Q, which is kilonewton per meter. So, finally, it will be kilonewton per meter square, because we are dividing by B, and this k 0 is kilonewton per meter square per meter. So, if I multiply with W, so this will be kilonewton per meter square per meter into meter. So, this will be kilonewton per meter square, and you come to this part, this E I is kilonewton meter square, then B is meter into d 4 means meter, meter to the power 4 divided by meter to the power 4. So, this will be kilonewton meter square. So, you can write these expressions any form, but when you write them properly, so that the dimension in the left side and right side will match. So, this way you have to express. So, then when you can write k directly, in that case this will be k into B actually, or k 0 into B. So, that means here you just express them in, you can express them in different form, but you have to express them properly. And another thing that remember that the k 0 units is kilonewton per meter square per meter, and k is B into k 0. So, k unit is kilonewton per meter square, but here k we are not using directly, we are using k 0 and we are taking B divided by two other parts. Okay. So, now this is your equation. So, finally, I can write the equation in this way, that if the beam with finite length or finite width, then this is the expression, and then I can finally write that if beam under plane strain condition, because this is beam with finite width, under plane strain condition this will be E star I d 4 W d x 4 plus k 0 W, this is equal to Q, because under that condition B is equal to 1. okay, because B will be under plane strain condition, and E star is equal to E 1 minus mu B square. Okay. So, I will solve these equation basically, beam under plane strain condition. You can solve the beam with finite width also, but in that case there will be a B value, but here I have taken B as a unit because it is under plane strain condition. So, my equation is this one, and then I will express that the similar way we can express as the dw dx for finite difference scheme is I plus 1 minus 2 wi plus wi minus 1 divided by, this is the expression, d square w dx square, I think d square w dx square. So, this is equal to h square, and dw dx is, this is the expression. Okay. So, I can write I plus 1 minus I minus 1 divided by 2h. Similar way, I can write d3w dx 3, that is equal to wi plus 2 minus 2i minus I plus 1 plus 2i minus 1 minus wi minus 2 divided by 2 h cube, and d4 w dx 4 I can write in central difference scheme is wi plus 2 minus 4 wi plus 1 plus 6 wi minus 4 wi minus 1 plus wi minus 2, that is equal to h to the power 4. So, these are the expressions of dw dx to d4w dx 4 in central difference scheme. So, now my equation is this one. So, that means here I have to write E star I, and this equation is w I plus 2 minus 4 wi plus 1 plus 6 wi minus 4 wi minus 1 plus wi minus 2. This is h 4, then plus this is k or k 0 wi, that will be equal to q I, because this is my equation. Okay. This equation I am expressing in finite difference form. So, now if I take all the coefficient in a bracket. So, coefficient of wi plus 2, or if I take this side minus, coefficient of wi minus 2, that coefficient will be E star I h to the power 4, then plus wi minus 1, this coefficient will be minus 4 E star I divided by h 4, then wi coefficient is from here it is 6 E star I divided by h 4, from here it will be k 0. Then this side from wi plus 1, this will be again minus 4 E star I h to the power 4, then plus wi plus 2, this will be E I or E star I h to the power 4, that will be equal to q I. Okay. So, now we have divided, suppose this is my beam, which is a finite beam, and UDL is subjected to UDL, and this is the center, and it is a symmetric problem. So, I can write this is point is x equal to 0. So, if I take these points only, and if I divide these points into number of nodes, this is first node, second node, third node, and this is my nth node. Okay, this is first, second, third, say nth node at x equal to L, or x equal to, I can write that this is my beam length. So, this is x equal to L by 2. So, this is L by 2, this is also L by 2. So, it is under plane strain condition. So, its B will be equal to 1, I have discussed. So, this is my different nodes. So, every node I have to apply these equation, these equation every node I have to apply. So, now the problem is I know the W I minus 2, W I minus 1. Suppose if I apply it is in third node, then W I minus 1 is the second node, W I minus 2 is the first node. So, there is no problem. So, up to onwards, up to third nodes and onwards, there is no issue. But if I want to apply them in the first node, then I have to get one I minus 2 node, that means minus 1 node, which is not present. So, that means for first node and second node, it is we cannot apply this, but from 3 nodes onward we can apply it. Similar thing will happen for nth node and n minus 1 node. Okay? So, from n minus 1 node. So, these 4 nodes we will have problems. That means, first node and the second node and the nth node and nth minus 1 node. These 4 nodes we cannot directly apply this equation, because we need more nodes to apply this equation on these 4 nodes. So, others node from 3 to n minus 2 node I can apply this equation, no issue. So, what to do? So, here we have to apply the boundary conditions. So, now it is a finite beam, free end beam. So, we have 4 boundary conditions. So, what is these 4 boundary conditions? Because here now we have taken the half portion of the beam and the loading is symmetric. So, boundary conditions are that as the loading is symmetric, so slope at x equal to 0 and it is UDL, and in the center shear force at x equal to 0 will be 0. Now, at the end, what is at the end? At the end, your bending moment at x equal to L by 2 will be 0 and shear force at x equal to L by 2 will be 0, because it is the free end beam. Similarly, hinged beam or the fixed end beam, you have to apply the boundary conditions I have discussed during semi infinite beam. So, accordingly to those boundary conditions you have to apply, but it is a free end beam. So, this at L by 2, x equal to L by 2, bending moment is 0 and the shear force is also 0. So, in the next class I will discuss that how I can apply these boundary conditions to solve these particular problems. So, this boundary condition is valid for this particular problem, where beam is finite length and it is a free end beam. Both ends are free and it is a symmetric condition. So, that is why you have taken only half portion of the beam. So, next class I will give you the idea how we can apply these boundary conditions and how we can apply these equation on these 4 nodes, that means node 1, node 2 and nth node and nth minus 1 node. Thank you.